All right, welcome back, everybody. Today we are going to begin our conversation about continuous random variables and probability density functions. So let's review for just a minute, and let's talk about our continuous random variable. All right, our continuous random variable has an interval of real numbers. So for example, a couple of examples of continuous random variables would be height or weight or even time, because they don't have discrete values. You can be 6 foot, you could be 6'1", you could be 6'1/2 inch, 6'1/4 inch, all of those values in between. Versus the discrete variable, well, for example, for a discrete variable, all right, an example would be like values on a dice. You can roll and get a 3, you can roll and get a 4, but you certainly cannot roll and get a 3.5. All right, so as I said, we're going to talk about continuous variables. Now, whenever we did a probability of a certain number, like x equals 3 for a discrete variable, and we had a variety of different ways to do that, depending on how the variable was distributed, we got a value. But with a continuous random variable, be very difficult to get exactly 3. For example, if you say it takes me 3 minutes to read 2 pages of a book, does it take you exactly 3 minutes, or does it take you 3 minutes and 2 seconds, or 3 minutes and 10 seconds, or 2 minutes and 55 seconds? So we do say that to get the probability of an exact number for a continuous variable would very often equal 0. Usually what we're doing is we're looking for kind of a range. So for example, I'll use my reading 2 pages of a book. If you claim it takes you 3 minutes to read 2 pages of a book, we're really looking at anywhere from, let's say, 9 minutes and 50 seconds to 10 minutes and 10 seconds. Somewhere in there would be reasonable. All right, so a continuous random variable is distributed with what we call a probability density function, or PDF, and has 3 requirements. The first one is that our function must be greater than or equal to 0 for all values of x. Our second thing is that the probability that a constant a is less than or equal to x, which is less than or equal to b, equals the integral from a to b. Excuse me, that's a terrible integral. F of x dx. Third requirement is that the integral from negative infinity to infinity of f of x dx equals 1. And that basically says that for all values where f of x is defined, if we add up all the probabilities, it should equal 1. All right, and just like with discrete variables, all right, it is assumed that f of x equals 0, where the variable is undefined. All right. So let's just jump right into our first example. Our first example says, let x denote the width in millimeters of metal pipes. From an automated production line. If x has the PDF, the probability density function. All right, so f of x equals 10e to the negative 10 parenthesis x minus 5.5 for x is greater than or equal to 5.5, or f of x equals 0 for x is less than 5.5. We want to find three things, and I'm going to state them one at a time. So the first thing we'd like to find, right, I'll call that A. The first thing we'd like to find is we'd like to find the probability that x is less than, not 5.5, just kidding about that, 5.7. All right, so why don't you pause the video for just a second, think about it, and we'll do the problem together in just a second. All right, hope you thought about it for just a second. And using the concept that we learned just a few minutes earlier, we can do the integral of our PDF, starting at 5.5, because that's where we start, and running to 5.7. And we're going to integrate our function. So our function is 10e to the negative 10 parenthesis x minus 5.5 dx. All right, I'm going to scroll up just a little bit. Try to keep as much on the screen as I can. And we got to do this integral now. Now this integral is a u substitution. So we're going to say that, I'm going to use a different color so we can denote the calculus from the statistics. So u equals negative 10 times x minus 5.5. du equals negative 10, or dx. And negative, right? Okay. And now we need to make our substitutions. So we can say that this equals the integral from negative, or not from negative, excuse me. The negative, right? The integral from 5.5, 5.7 of e to the u du. And then it's negative integral e to the negative 10 x minus 5.5 dx. So when we do that integral, we wind up with, right, so 5.5 to 5.7. And now when we do the integral and we execute the fundamental theorem of calculus, we get negative e to the negative 2 plus e to the 0. And when I do that out, I get 0.865. So that is the probability that the width of our pipe will be between 5.5 millimeters and 5.7 millimeters. All right, now the second thing I want to do with this same problem, and I'm going to call that B, is I'd like to know the probability that our width is greater than 6 millimeters. All right, now we're going to set up the integral a little bit differently, and this time I'm just going to let you do the integral. So our integral is going to be set up, we're going to start at 6, and we're going to go to infinity. And again, we're going to integrate our function. Our function is 10e to the negative 10 times x minus 5.5 dx. All right, so I did the u substitution for you last time. Again, it's another u substitution. Why don't you pause the video, give it a try, and we'll talk about on the back end. All right, so if you did your u substitution, you should have gotten negative integral 6 to infinity e to the u du. All right, which then when you do the integral, you get negative e to the, I'm going to substitute right back in, negative 10 x to the minus 5.5 from 6 to infinity. Now, because our exponent is negative, right, we can transfer that directly to the denominator of our fraction, which means that when I plug in an infinity, I get 1 over e to the infinity minus 1 over e to the 5th. And that would equal 0, actually plus, excuse me, plus 1 over e to the 5th, which I got 0.007. So it doesn't look very likely that the width of our pipe would be more than 6. Now the third situation I want to do is I want to find out, and I'm going to call this C, and I'll use a different color. I'll use blue, what the heck. All right, I'm going to call that C. I want to know the probability that the width of our pipe is going to be between 5.6 and 6 millimeters. All right, so again, I'm going to help you set up the integral. So we set up the integral by saying the integral from 5.6 to 6 of 10e to the negative 10 x minus 5.5 dx. At this point, I'd like you to pause the video, do the integral, and we'll take a look on the back end. See you soon. All right, once again, it's a u substitution. So, and the answer I got was 0.361. So that is the probability that the width of our pipe will be between 5.6 millimeters and 6 millimeters. All right, so I gave you while it's only one problem, there was a definite variety of situations there. Hopefully you got a lot out of that, and we'll definitely practice some more when you get to class. All right, so now we're going to move into 4.2, and we're going to talk a little bit about the cumulative distribution function. Or CDF of the continuous random variable. All right, for this, we're going to use similar type notation. All right, so for the cumulative distribution function, I'm going to use big F of x. All right, and basically what that is going to be the integral of our PDF from the last section. So if we integrate our PDF, we get our CDF. All right, now notice I'm integrating from negative infinity up to as high as it goes, so it could be up to infinity, but of course that would not be very realistic. So if our variable has restricted values, all right, we simply need to, to get our big F, we simply need to integrate from the minimum value to the max of, I'm going to call it t because I called it t before, dt. All right, let's jump into an example. So we let x be a random variable. With a PDF of 5 for the values 4.9 to 5.1. So the question is, find the CDF of x. So if we're going to find the CDF of x, we need to integrate 5. All right, and when we integrate 5, we get 5x. So here's how I would write my final answer. My big F of x is going to be, and I'm terrible at writing those big squiggly brackets, so is 0 for x is less than 4.9, 5x for 4.9 less than or equal to x, 5.1, and 0 for x is greater than 5.1. This is indeed the best possible answer. I've seen it a couple of other ways. I probably will show you a few of those ways right here in this video. All right. So let's go to an applied example. Suppose the PDF of X of a dynamic load on a bridge is you know what? I'm not going to squiggle it. Can if you want to. I'm not doing it. So 1/8 plus 3/8 x for 0 less than or equal to x less than or equal to 2. And every other place it is 0. So we are looking for the CDF. So find the CDF. All right. So if we integrate, so my big F of x, my CDF function, is going to be the integral from negative infinity up to x of 1/8 plus 3/8 we'll call it y, so we can distinguish the variable, dy. And when we integrate, we get x over 8 plus 3/16 x squared. Thus, the CDF, denoted as big F of x, is going to be 0 when x is less than 0. Is going to be x over 8 plus 3/16 x squared when 0 less than or equal to x less than or equal to 2, and is going to be 1 when x is greater than 2, because once we're greater than 2, we've accumulated all the probability we're going to get. All right, so there is our CDF. And now we want to find the probability, so part B of our problem. Find the probability that the load is between 1 and 1.5. All right, so for this, right, we're going to use our CDF, because if I say I want to know the probability that our load is between 1 and 1.5, I would integrate my probability density function, which I've already done. So it's just a matter of executing the fundamental theorem of calculus, which would say do big F of 1.5 minus big F of 1. So why don't you pause the video? I'll scroll down just a little bit so you can see the function. And why don't you execute the first fundamental theorem of calculus, and I'll get you the answer on the back end. All right, hopefully you've done it. And I'm going to scroll up a little bit. As a fraction, I got 19 over 64. And you can round to the thousands, saying 0.297. So that is your probability that our load is between 1 and 1.5. All right, part C of our problem now is going to say what is the probability that the load exceeds 1? So what is the probability the load exceeds 1? Very similar strategy. But we're going to set it up a little bit differently. So I want the probability that x is just greater than 1. All right. Well, again, I want to use my CDF. I'm just going to use it in a slightly different way, right? If the load exceeds 1, but remember, it can go up as high as it wants to go, right? Our function goes between 0 and 2, but after 2, we still keep going. So if I do 1 minus the probability that x is less than or equal to 1, I should get everything else. So in order to get that, I would do 1 minus my cumulative probability up to 1. Remember, the CDF is a cumulative probability, so the probability from 0 up to 1 would be big F of 1. So why don't you take that 1 and plug in. I'll actually rewrite the function for you. I got 1 minus 1/8 I'm going to scroll up a little bit, times 1 plus 3/16 times 1 squared. I plugged in the 1 for you. All right, so why don't you pause the video, do the math, and we'll get back together on the other side. Alrighty. I got an answer of 11/16, which rounded to the thousandths, 0.688. All right, so when we're using our big F of x to compute probabilities, a couple of things to remember, all right? So that is that the probability, right? X is less than A. You want to do 1 minus big F of A, right? And these are things that we saw in the last problem. And the probability that A is less than or equal to X, which is less than or equal to B. All right, as long as we have the CDF, we want to do big F of B minus big F of A. Hopefully that these two ideas will be really helpful as you're looking to do some problems. All right, so I got one more thing that I would like to talk to you about, and that is finding percentiles. This is something that could come up. All right, so I think it's best explained by maybe trying to do one or two examples, all right? So I'm just going to outline an example. Let's let x be a continuous random variable with the following PDF. F of x equals, I'm just going to say 1/2, very basic example, but hopefully it will give you a good idea of what we're doing. 4, 0, less than x, which is less than 2. So the question is, what is the first quartile? Median and third quartile. All right, so now there's a couple of different ways we can show this. We can show it via a graph. So if I create a very small graph, there's 0, there's 1, there's 2, and I'm going to go up, I'm going to call that 1/2, right? And our PDF is a uniform function. So I'm going to try to make a nice straight line for you. Let's see if I can do it. There's a nice straight line. And I'm going to try to make one more. There we go. And there is our uniform function. Now, if we're looking for the first quartile, right, that would be 1/4 of our rectangle. So our first quartile would come right about here, and this would be 1/2. So our length would be 1/2 and our width would be 1/2. So the area of that box would be 1/4. So there is our first quartile. All right. Now for the median, again, we want to know how much half of our rectangle is, how much area that holds. And for that second part, it holds 1/4 of our area. And for the third quartile, again holds 1/4 of our area, because the entire rectangle has to hold an area that equals 1, right? That is how much area we need to have. So that's how you show it geometrically. The way you show it numerically is this. So we're taking a look at our CDF, which means we need our big F of x. So I'm going to integrate from 0 to x, 1/2 dt, which equals 1/2 t from 0 to x, which equals 1/2 x. All right, so we got our big F, right? We have 1/2 x. I'll call that, I'm running out of room, so I'm just going to call it x/2. for 0 is less than x, which is less than 2. All right, so in order to find our Q1, we're going to say that 0.25, which is the amount of area we need, is going to be big F. And I'm not 100% sure why they use pi, but they use pi as the symbol that we need of, right, the number we need to put in for our Q1. All right, so we can plug that into our function. Our function says 0.25 equals, right, and our function is 1/2. F of 0.25. And if we get our number by itself, I'm going to multiply both sides times 2. Right? So F, I'll call it Q1 equals 0.5, which is how much area we had there. All right, so for our median, right, our median means we have half of our area. Half of our area is 1/2 equals F of, again, not sure why they use that as the variable, but they do. So we now need to plug that into our function. So 0.5 equals 1/2. Pi of 0.5. And when we multiply both sides times 2, I get 1. And then if we want to do Q3, I do 0.75 equals F pi over 0.75. So that equals, right, plugging it into my function, 1/2. Actually, if you don't mind, I'm going to change that to 3/2. Multiply both sides times 2 to get our variable by itself. Sorry, that should have been 3/4, not 3/2. I gave away the answer because when I multiply both sides times 2, now I get my 3/2. All right, so there it is. All right, so there is our third quarter is 3/2. And I just want to leave you with one last idea. And this idea was probably wrapped up in our talk from before. But if we wanted to move backwards, let's say we wanted the little f, the probability density function, right? But we're given big F. We just need to do the derivative of our big F to get our little f, provided the derivative exists. Okay, so thank you for listening. I know this was a slightly longer one. We covered an awful lot of material. I hope you enjoyed the video. Come to class. We'll do plenty more practice. Thank you. I look forward to seeing you guys soon.